This chapter is called orthogonality. In this chapter, we're going to learn about orthogonal vectors, orthogonal subspaces, direct sums of subspaces, and different inner products. So to start off, let's define some terms. So suppose we have two vectors in Rn. I'm calling them x and y. And x is going to be this column vector, x1 through xn, and y is going to be y1 through yn. Now, if we try to multiply these two vectors, this can't be done because this is a n by 1 vector and this is an n by 1 vector. And remember to multiply two matrices because that's what they are. These two numbers have to be the same, and unless n is 1, you can't multiply them. So this does not exist. However, we can take the transpose of one of these, and I'm going to take the transpose of x, and I'm going to multiply it by y. And this is x1, x2, all the way to xn, times y1 through yn. And this is just the dot product, which you can say is the dot product, or you can call it, which the book calls it, the scalar product in Rn. And we could also abbreviate this as I is equal to 1 to n of xi, yi. So this is the scalar product in Rn. The next thing I want to do is I want to write this a little differently. I am going to define this notation. You can see these fancy brackets here. Whenever you see this, at least right now, in later sections we might define it differently, but whenever we write this, what we're saying is we want to take x transpose and multiply it by y. What is the norm of a vector? If you see this notation, x with two straight lines on both sides, what you're going to do is you're going to take the square root of x transpose times x. So again, if x is equal to this column vector, x1 through xn, then the norm of x is the square root of xi squared. I is from 1 to n. Just write it out here so you can see that. And you could also, instead of putting the square root, if you like, you can just raise it to the power 1/2. Let's look at some properties of the inner product. So the inner product takes a vector in Rn and we're multiplying it by another vector Rn, and what we're doing is we're spitting out a number. So the first property is it's symmetric. Let's prove that really quick. So on the left-hand side, this is equal to x transpose times y, which we said is x1 through xn, y1 through yn, and we get this finite sum. But we can switch these two. This is equal to yi, xi, because they're real numbers, and we know real numbers commute. but you could also write it like this. And also, for some reason, I write my y's two different ways. Sorry about that. If that confuses you, just sometimes I write it like this, sometimes I write it like that, and they're not different y's. Anyway, so that's one property, is that this inner product, the scalar product, is symmetric. Another property is if we have a scalar and we multiply it with the vector, let's say the vector x, we could also just take that scalar out and multiply these two, take the inner product of these two vectors and then multiply it by the scalar. Or we could take the scalar and multiply it by the vector y and then take the inner product of x and alpha y. We can prove that as well. So let's do the left-hand side, this alpha x y. So we know that this is alpha x1, alpha x2, all the way to alpha xn, because when we multiply a scalar times a matrix, that scalar goes to everything inside the matrix. Oh, but this is the transpose, so let's make sure we transpose that. And then multiply it by this vector. This is the sum, from I is 1 to n, of alpha xi times yi. But you can see from here that I could move these parentheses because real numbers are associative. So we could write it like this. And if we have a number that doesn't have an I, we can pull it outside of the sum. Which is this second part right here. So we proved this. But also, we can move scalars around. So this piece right here, we could put it back, this alpha back behind this sum, and then we could write it like this. There's no problem doing that. These are just numbers, so we can move them around. But then that is just the inner product of x and y, alpha y. So we get this last piece here. Another nice property is if we have x and y in Rn, and A is an n by n matrix, then A times x, if we take the inner product of that with y, this is going to be the same as x, A transpose with y. Now this one's a little different because when we had a scalar, we could just move it to the back here. But we can't do that here. We have to actually take the transpose. Well, let's prove that. So the left-hand side, ax with y, well, we take the transpose of what's written here and multiply it with y. Well, what happens when we take the transpose of two matrices being multiplied together? Remember, if we have B times C, we take the transpose. This is C transpose times B transpose. So we get X transpose times A transpose times Y. And you can put the parentheses here if you like, that's fine. But remember that with matrices, they are associative. So now we can put the parentheses here. And what is this? This is X transpose times this. This is going to be a column matrix. Let's let's just make sure. So if we have a, which is n by n, we multiply it by x, which is n by 1, this will end up being, well, we have n and n, we're left with n and 1, so this is a matrix, let's call it B, which is n by 1, which is a vector in Rn. But if we take the transpose of this matrix, it's also going to be n by n, and if we multiply it with a n by 1 vector, again, we can cross these out, we're going to get some n by 1 vector. So this is okay, what we're doing, and we're left with x, comma, aty. So this is true. The next thing we're going to talk about is the distance between two vectors. So say we have two vectors in Rn, then the distance between them is given by taking the norm of x minus y. So you can write it this way if you like, or you can say the square root of x minus y transpose times x minus y. Let's do an example of this. So let's find the distance between these two vectors in R3. Okay, so we're going to first figure out what x minus y is. So this is 1, 3, 0, subtract 2, 2, 5, 1 minus 2, negative 1, 1, negative 5. Okay, now we're going to take the length, or the distance between x minus y, which is the length of this vector. So this is the square root of this one squared plus this one squared plus the last one squared. So this is 25, this is 1, and this is 1. So we get the square root of 27. Maybe I shouldn't put two lines there because I have two lines here. I'm going to circle it instead. So that is the distance between these two vectors. Now you can do this for Rn. Remember, if we have n things here and n things here, you would just subtract them like we did here and then square each piece. So square this one, and all n of them, add them together, and take the square root.